last thing we need to talk about here is we've talked about how you do the derivative of a logarithmic function to whatever base you want. Now let's talk about how you're going to do the derivative of an exponential function with whatever base you want. So this is actually the question that I started the last lesson with right at the beginning of this unit. I said, if you've got something y equals a to the x, where a is just some constant that represents your base, how do you find the derivative of this? And so we tried to do this from first principles, and what we got was, we found that our derivative was the original function, a to the x, times this limit as h goes to 0 of a to the h minus 1 all over h, that we didn't know how to evaluate. So that's what set us off trying to evaluate it numerically, which led us to the value of e, which made this thing very, very simple. So what happens if you're not using e as your base, so everything doesn't work out very, very simply? Okay. What we're going to do is we are going to use this thing that I used when we were doing the logarithms. That if I have e to the ln of something, I'll just say I've got p right here. Okay, that's just going to equal p because I can sort of cancel out the e and the log to the base e there. Okay. So we can use that to rewrite our original function a little bit. We start with y equals a to the x, and I'm going to rewrite that as something with the base e, because I know how to do derivatives if my base is e. So I'm going to write this as e to the ln of a to the x, because the e and the ln will cancel out. I'll just be left with my original function. I can apply my laws of logarithms up here in the exponent to bring the x out in front. So this becomes e to the ln a. But just like when we were working with the logarithms, ln a, because a is just some number, this is just a constant. So to emphasize that, let's just rewrite this slightly. E to the ln a times x, where ln a is just some number. We know how to take the derivative of this. Okay, we've got a composite function. Okay, we've got this function ln a times x up in our exponent. So we know that we're doing the derivative of the exponential function. We get the original function back multiplied by the derivative of what's up in the exponent. Well, the derivative of ln a times x is just ln a. Now we can undo what we did to our original function. This is e to the x ln a times ln a. Or I can move the x back up into the exponent. So this is going to be e to the ln a to the power of x times ln a. But again, the e and the ln just cancel out. So I'm left with a to the x times ln a. So the derivative of y equals a to the x is a to the x times ln a. Ln a is just a number. And this is what we expect to get. Because way up here, when we did it from first principles, we got y primed is a to the x times something, which is a number. What is that number? It's going to be the ln of whatever your base is. Okay? So y primed is a to the x times ln a. I'll just say if y equals a to the x. So that's our next derivative rule here. And of course, if y is a composite function, a to the g at x, then our derivative is going to be, well, similar to when we did with the base e. We get our original function, so a to the gx. Okay. We have to have this numerical factor in here, ln of the base, to account for the fact that we've got a base other than e. And then we still have the chain rule, which tells us we have to multiply by the derivative of that inner function. So if we've got a to the g at x, our derivative is y primed, which is equal to a to the g at x times ln a times g primed at x. And that is the last sort of rule that you need to know in this unit. So the four things that you need to know for the test are derivative of exponential function with base e, derivative of an exponential function with a base that is not e, derivative of a natural log function, derivative of a logarithm that is a base other than e. If you know those four things and you can combine them with the chain rule, like we're doing here, that's all you need to know. Okay? So let's take a look at, let's do a couple of quick examples here. I got 4 of them here. Let's do 3 of them maybe. The first one is super short here. We've just got y equals 2 to the power of x. So we just need to apply the law. Y primed is going to be our original function, 2 to the x, times ln of the base, and we're done. Okay? That was just our original law. Okay? So we get our original function back, we multiply it by the ln of the base. Okay? So the next one here, we've got a bit of chain rule happening here. Our function f at x is 3 to the exponent x squared plus 2. So let's identify first what is that inner function g at x. Well, it's up there in our exponent. It's going to be x squared plus 2. We're going to need the derivative to do the chain rule, so g primed at x is just 2x. So our derivative, f primed at x is, well, we had the original function, so 3 at x squared plus 2. Okay, so our original function, a to the g at x, multiply times the ln of our base, so ln, not 2, but ln 3. And then to finish off the chain rule, we multiply by the derivative of that function that's up in our exponent, or g prime. So we multiply that whole thing by 2x. And there's our derivative. Right, let's do this example number 3 here, and that's where we'll end it. So get this out of the way. All right. So f at x equals square root of 3 to the x divided by x squared. We should probably rewrite this one to make it a little bit easier. Nick. 3 to the power of x over 2, exactly. 3 to the power of x over 2. So taking that square root, turning it into an exponent 1/2, and combining it with the exponent on the 3. And rather than doing the quotient rule, because we have something divided by something, I'm going to rewrite this so we can use the product rule. So rewrite my 1 over x2 to x to the negative 2. So we've got two functions multiplied by each other. u and v. We're going to use the product rule. So our derivative, the first thing we need is u primed. So u is our exponential function here. So how do we take the derivative of this exponential function? Well, I use chain rule here. So first thing we have is the original function, 3 to the x over 2. We have to multiply that by, well, by what? To take into account our different base, ln of 3. We then have to multiply that by the derivative of what's in the exponent. So we've got x over 2, or 1/2 x, which is going to give us a factor of. If I have 1/2 x, and I take the derivative, just 1/2. Okay. That all gets multiplied by x to the negative 2. And for our second term, we need u. And that gets multiplied by v prime. So v primed is just going to be negative 2 times x to the negative 3. Simple power law. Now let's look and see what we can factor here. You can always factor something out of these exponential derivatives because when you take the derivative, you get the original function back. So this part of this original function will always appear in both terms. So we can factor out the 3 to the x over 2. And what else can we factor out? We've got a power of x in both of them. So let's take out the lowest power of x. And that's going to leave us with ln 3 times 1/2 times x, because we factored out x to the negative 3, so we add 3, yeah, we get 1. And then just the minus 2. Okay. Okay. And then we could just clean this up a little bit. How can we clean this up a little bit? I can bring my x cubed down to the bottom, keep my 3, can change this back to the square root of 3 to the x. Then my square brackets are going to be, I'll just write this as 1/2 ln 3 times x minus 2. And that's probably as simplified as I can get it. Something like x over 2. Nah, not a big deal. Because if I think of where I'm going from here, I might have to set this equal to 0 and solve. So I can solve what I have in the square brackets just by setting it equals 0 and rearranging. You could, if you wanted to, factor out that 1/2, and that would get you one more step here. If I factor out the 1/2, this stays the same. I have ln 3 times x minus 4, because I've taken out a factor of 1/2, which doubles that 2, and then I get a 2 down here. But yeah, at this point, I'm more interested that you can do the logarithmic and apply the chain rule correctly. Okay. So I think that's a good place to